What's up, music nerds? Welcome back to Chapter 5 of Hermann Helmholtz on the Sensations of Tone. Last week we left off with plucked or struck strings, and today we're picking back up with bowed strings. The link to the webbook I'm reading from is in the description. You can find the entire text of the book there, as well as all the apps that I'm going to show you in this video. So let's get to it. 4. Musical tones of bowed instruments. No complete mechanical theory can yet be given for the motion of strings excited by the violin bow, because the mode in which the bow affects the motion of the string is unknown. I can't imagine this is true anymore, but Helmholtz used this vibration microscope to observe the vibration of strings. This is a tuning fork in here. And there are magnifying lenses right here at one end of the prong. He's looking at a fixed point of light through these lenses. When the tuning fork is set in motion, the lenses are vibrating in a simple pendular vibration, making the point of light appear like a line. So then if you attach the point of light to a vibrating string, which is vibrating horizontally, then when its period is exactly 1, 2, or 3 times that of the tuning fork, we can get an image in the microscope like these images here. A through A is what we would get for a simple pendular vibration, like capital A over here, and B through B is what we would get for a violin string tuned to the same as the tuning fork on capital B here, and C is what we would get for a violin string tuned to an octave above. We get these forms if we imagine the curve sort of pasted on the outside of a clear glass, and then when you turn the glass, these would be the images you see. This app helps us to visualize that. Here's the A curve, simple pendular vibration. And this is what we would see in the vibration microscope at different phases. Here's B curve. And C. So now he's taken the images from his vibration microscope and flattened them out, so to speak, to get these curves for the motion of the string at a quarter of the way down, and this is even closer to the end of the string. As we can see, the point moves further and further to the right. This app allows us to see how these experiments of the vibration of the different parts of a violin string might look and sound. Here's right in the middle. And we move the point further to the right. Even further. And let's try to the left. So now that he has the vibrational form of the bowed string, he can calculate the intensity of the upper partials mathematically. The prime in the compound tones of bowed instruments is comparatively more powerful than in those produced on a pianoforte or guitar by striking or plucking the strings near their extremities. The first upper partials are comparatively weaker, but the higher upper partials from the 6th to about the 10th are much more distinct and give these tones their cutting character. Let's try and hear some of this with the bowed string app. Let's try a pretty low note. Let's listen for that upper partial. What about this one? I can definitely hear those higher harmonics easier on the bowed string than I could on the plucked string app. All right, moving on to the musical tones of flutes or flute pipes. In these instruments, the tone is produced by driving a stream of air against an opening, generally furnished with sharp edges, in some hollow space filled with air. The motion of the air that takes place in the inside of organ pipes corresponds to a system of plane waves which are reflected backwards and forwards between the two ends of the pipe, which means that tones of wavelength double, triple, quadruple, and so on, the prime of that, are reinforced. So that's the same harmonic series of the upper partials of a string. However, for pipes with a closed end, the period is twice as long, so the phase of those reflections cancels out for even partials. Hence, the tones of strongest resonance in stopped pipes correspond with the series of unevenly numbered partials of its fundamental tone. Number 6, musical tones of reed pipes. These are similar to the siren from Chapter 1. A tone is produced by the passage of air being opened and closed by the movement of the reed. And these are divided into 3 groups. 1, the reed pipes of organs and vibrators of harmoniums, pictured here. And this is how they sit in the pipes of reed organs. Number 2 is the tongues of clarinets, oboes, and bassoons. Clarinets have 1 reed vibrating against a mouthpiece, and oboes and bassoons have a double reed which opens and closes. And number 3 is membranous tongues, and this includes your lips when playing a brass instrument and your vocal cords themselves when singing or speaking. But here is an artificially constructed one, which is a cylinder of wood with some rubber strung across it. So the difference between these 3 categories. Reed pipes, each reed gives only 1 pitch, so the reed is comparatively stiff and heavy. The tongues of reed instruments like clarinets, oboes, and bassoons are lighter and more elastic. We can set the air in the body of the instrument into vibration at various proper tones by increasing the pressure of the air against the reed. And of course, the keys on the instrument allow us to hit every note chromatically. Now, the proper tones of the reed itself are really high. Helmholtz can hear up to the 16th or 20th partial. If you've ever heard someone blow a double reed on its own, it's pretty screechy. Horns and trumpets, it's the same idea, but the tube itself is much longer, so the prime tone is much deeper, which means we can hit more notes of the scale as we're going higher in the upper partials. And of course, modern trumpets have keys as well, so we can hit every note chromatically. And horn players change which partial speaks by changing the tension of their lips. Now, for your voice, we change all of that all the time, not just the tension of the chords, but how thick they are, the size of the resonating chamber. All of that is elastic, all of that is changing, and that's why your voice is so much more agile in terms of the quality of sounds you can make than any other instrument. Case in point, vowel qualities of tone. The more the mouth is narrowed, either by the lips or the tongue, the more distinctly marked is its resonance for tones of determined pitches, and the more, therefore, does this resonance reinforce those partials in the compound tone produced by the vocal cords, which approach the favored pitch, and the more, on the contrary, will the others be dampened. Hence, on investigating the compound tones of the human voice by means of resonators, we find pretty uniformly that the first 6 to 8 partials are clearly perceptible, but with different degrees of force according to the different forms of the cavity of the mouth, sometimes screaming loudly into the ear, and others scarcely audible. Now, of course, he was experimenting with German vowel sounds, so we'll have to trust our translator here. First series of vowels is with the lips pursed. U, O, O. And the mouth is a bit more open for each. And with resonators, he determined these pitches. Then we have ah as in father, the most open vowel, followed by the second series, which is open at the back of the throat and constricted by the tongue and the hard palate. A, E. And these tones have two proper tones, one for the back of the throat and one for the constriction point by your tongue and your mouth. So the resonant tones split, one going up in pitch and one going down. And finally, the third series, which seems to be sounds that sort of only exist in French and German, but they have the constriction with the tongue and also with the lips. And ü. If you speak French or German, tell me in the comments if I said that right. And that brings us to the end of this behemoth of a chapter. Helmholtz has distilled it down into some general rules about quality of tone. 1. Simple tones have a very soft, pleasant sound, free from all roughness, but wanting in power, and dull at low pitches. 2. Musical tones which are accompanied by a moderately loud series of the lower partial tones, up to about the sixth partial, are more harmonious and musical. Compared with the simple tones, they are rich and splendid, while they are at the same time perfectly sweet and soft if the higher upper partials are absent. To these belong the musical tones produced by the pianoforte and open organ pipes. The human voice and that of the French horn form the transition to musical tones with higher upper partials. Number 3, if only the unevenly numbered partials are present, as in narrow stopped organ pipes, pianoforte strings struck in their middle point, and clarinets, the quality of tone is hollow, and when a large number of such upper partials are present, nasal. When the prime tone predominates, the quality of tone is rich, but when the prime tone is not sufficiently superior in strength to the upper partials, the quality of tone is poor. Number 4, when partial tones higher than the sixth or seventh are very distinct, the quality of tone is cutting and rough. The most important musical tones of this description are those of bowed instruments, of most reed pipes, oboe, bassoon, harmonium, and the human voice. The rough, braying tones of brass instruments are extremely penetrating and hence are better adapted to give the impression of great power than simple tones of softer quality. Why high dissonant upper partials should make a musical tone more penetrating will appear hereafter. So come back next week for Chapter 6 to find out why. And until then, check out sensationsoftone.com where you can play a little virtual violin. That way you don't have to deal with the steep learning curve of playing an actual violin. And I will see you next week. Bye!